Hello everyone, I'm Si Chen. I'm currently a PhD candidate of spatial informatics at University of Illinois at Urbana-Champaign. And today I'm going to introduce this project, which try to use a new approach to do park classification. So park classification is basically is a required information and framework for doing the urban planning scenarios, especially the land use and green space system plans. But there are some issues in current park classification. So typically, all the parks in our study area, they are typically classified based on the local planners, their knowledge, and they manually do the labeling and they do the field observation. And then they decide some empirical benchmarks like the park size and their park views and their services and activities they can observe from the parks. Then this park classification will be decided. And so such kind of approach is kind of not efficient and subjective and also very subjective. There is some very recent researchers, they started to realize this problem and they try to use some new data source. For example, the social media text data or tracking data and to extract park information and to support better park classification. But the geolocated images, they are kind of not very frequently being used in these recent studies. There are some reasons why the geolocated images are kind of ignored in these studies, because image data sets for parks, they can be very sparse and also have very varying quality, and they can come from diverse points because they typically come from their local planners, their field trips, or they come from the social medias. And also there are similarities between images, even in different park classification, they are naturally high. And except the specific issues in park classification, there is some broader issue in urban models, especially the spatial models. So in terms of those large-scale urban models, they are usually very spatially sensitive. And also when they are applied to new areas, their data requirements are high, but their local data set from urban planning departments are usually not able to support the running of these large-scale urban models. Then they have the data hungry problem. And within this urban models, typically there are some complicated model parameters, and they are trained just to a specific task. And all of these problems, they hamper the adoption of urban models across different urban settings. And few studies have explored some universally applicable approach to replicate and adapt urban models across different domains. Right now, the replication and adaptation of urban models are still mostly rely on the manually rescaling and manually data processing by the model runners. And to address all of these specific issues and also the broad issues. So in this project, my goal is to apply deep learning approaches to decrease the obstacles that hamper the replication of urban model across different urban settings, which include the spatial sensitivity, data hungry problems, and also the highly complex model parameters. And here, the park image classification framework, it serves as the first step and also our case application to test the efficiency of the proposed approaches to model replication, and also to address the issues in park classification system. So before we start to introduce the methods, I wanted to like start from the challenges to classify the park images. So the first challenge we met was the park images. They looks very similar from human observations. It's usually difficult to tell the difference between the park photos, which actually have quite different classification labels. So here we give some examples. For example, between the community park and neighborhood park, they look nearly exactly same from our eyes. And also the image size and the resolution varies a lot. So as I talked, so the park images typically in our city or in our region, they come from the social media platforms, or they come from the field studies by the local planners. And this then it has resulted the highly varied image size, resolution, and even brightness of these park images. And also typically when for our city and or for our region, it typically usually have just hundreds or thousands of park images overall. But the image processing models, they usually only can perform well on very large data set. For example, the deep convolution neural networks, which is one of the most state-of-the-art method in image processing. It usually requires like much more images to guarantee the good classification result. And that is the third challenge we met. And also the fourth challenge was the application to different city environments. So for when we propose this park classification framework, and we don't want it only can be applied to our the single context, like to our study area. We expect it could be easily replicated and adapted to like new study areas. So that would then it require it has some like data processing, rescaling, and parameter concerns during its replication and adaptation of the models. And our methods, so specifically like to increase the replicability and adaptability, we try to use the transfer learning approach and to transfer the knowledge from the main domain and to the target domain. So the model training does not need to begin from the scratch. And through doing that, the model could have lower data requirement and also like lower hardware environment requirement, but at the same time, it can maintain a valid model performance. So through doing it, we can reduce the data and data manipulation requirement and lower the time and resource required for model operation, and then increase replicability and adaptability. And except the transfer learning, and we also combine the data augmentation strategy and fine-tuning strategies with transfer learning, and to further decrease the overfitting problems caused by the small data set. So here is our like logic for transfer learning. Like we got some generic features of the data set from the main domain, and then transfer these generic features to the target task. So in the target task, only the discriminative features of that target data set need to be started. And then we try to test the proposed approaches, like in improving model replicability and through its application in the park classification framework. And we choose City of Seattle as a study area. And they have our open data set with 55 geotagged parks and only 122 images overall. And that means for each park, there were only 2 to 4 images. And that is small enough, right, to test the performance of our proposed framework. And overall, it has 4 ground truth classification labels and recreational, like area, nature area, and community park and neighborhood parks. And between the community park and neighborhood parks, they look very similar. So that is, well, the challenge we have talked. And our model process, because each park, they have a group of image. So we propose, we design 3 deep CNN-based framework and to do the individual image classification. Then we aggregate the results of a group of image to each park. So also we design 3 aggregation results and test them. And finally, we obtain the best combination of the designed deep CNN framework and the aggregation method, and form the final park classification framework. So in the first model, we design it is mainly to let it serve as a baseline. And for model 1, we only apply our pre-training process to our classical DeepCNN model called VGG16. And here we use ImageNet, which contain 1 million images and have 1,000 object classes for the pre-training. And through the pre-training, this VGG16 framework could firstly obtain generic image descriptions and then apply to the target city's small park image dataset to learn the local features and without training from scratch. And so for model 2, so we plus our data, so this is model 1. And for model 2, we added our image augmentation strategy, and the model 2 still have the same structure with model 1. They both based on the VGG16 DeepCNN framework, but it contains our extra image augmentation strategy. So we try to throw distorted and flip the images and then to fabric some image and extend this very small data set and to decrease some of the overfitting problems. And in model 3, while keep the same structure with the previous 2 models, it add a fine-tuning strategy. So that means some convolutional layers, they are retrained according to the local data set. So through this processing, more discriminative and local features of the target city's data set could be learned. And for the aggregation of the individual image and into individual image classification results to each park, and we also designed 3 aggregation methods. So the first one is just a simple one, work as the baseline. It just chooses a frequently appeared classification label within each image group and assign that label to the park. And the second aggregation method was sum of probability. So here we try to sum the probability of each individual image classification results within our group, and then choose the label with the highest summed probability for each park. So through doing it, we consider the classification confidence for each individual image. And in the third aggregation result, we try to sum the squared probability of individual image classification results. So here we try to assign a bigger weight to those individual image classification results, which has higher confidence. And through like testing, we do the epoch training and testing, and we found the model 3 had the best result for the image classification result. So like we can see model 3, although it has some level of overfitting, but the overall accuracy was the best. And for model 2, the data augmentation did decrease overfitting problem significantly. And the model 1 worked as the baseline model. And also we further tested the 3 aggregation results, and finally we found the model 3 plus some of the squared probability, they are the best combination. And the final accuracy for the park classification achieved over 73%. And considering we only have 122 images for the 55 parks, this result is quite satisfying. So we try to use the deep learning approaches and to process the image, to process the park information in a more efficient and objective way compared with the convolutional manually labeling method. This can save the time and also can guarantee some relatively objective classification for the parks and to serve the better land use and green space plans. And also in urban planning field, the transfer learning methods used here also inform a potential way to train the model in our main city and then apply the model to our new city and achieving the easy cross-city replication and adaptation of urban models. And in next step, we try to not only rely on all the ground truth classifications, we try to use some weakly or unsupervised classification methods to automatically cluster or subclassify the parks and to achieve even more objective classifications. And also we will evaluate the whole model framework to other data set and to guarantee the model performance is not sensitive to this specific data set. Thank you. That's all my presentation. And other questions and comments are welcome.
Great. Thanks, Chen. And is there any questions? Yeah, we have one question from the chat box. So can the proposed model generalize to other image classification tasks?
Yeah, I think so. So as I talked, so this park image classification task is just the first step. And in next step, we will try to test it in different image data sets and for different types of places of interest.
Okay, cool, great. So actually, I also have a question. I saw that we have some new audience coming, and could you please clarify why do you need to classify the park? So is there any applications based on this, based on your approach or project?
So, well, my background is from urban planning, and in the practical urban planning process, park classification is the basic, it provides the basic principle for land use plan and green space and green infrastructure plans. So park classification represents the functionality and services of parks. And when we do the spatial plans for the city, we have to have such kind of information. Otherwise, it's just like the foundation for such kind of physical plans will be absent. So that is meaning for practical urban planning process.
Great. Yeah, thank you. So if consider about the time, if you have any further questions, you can email with Chen in the offline.